Construction is the art and science of creating structures that stand the test of time. From towering skyscrapers to intricate underground tunnels, these structures rely on a fundamental element, a solid foundation. The ground beneath our feet, however, is not always as stable as we might hope. Weak or unstable soil conditions can pose significant challenges to construction projects, jeopardizing their safety, longevity, and overall success. Ground improvement techniques have emerged as essential solutions to address these challenges, transforming weak soils into robust foundations capable of supporting even the most ambitious structures. By modifying the engineering properties of the ground, these techniques mitigate risks, enhance stability, and pave the way for innovative and sustainable construction practices. This essay delves into the world of ground improvement, exploring its significance, various methods, and real-world applications. Imagine constructing a high-rise building on loose, sandy soil. The weight of the structure would likely cause the soil to compress unevenly, leading to settlement, cracks, and potential structural failure. This scenario highlights the critical need for ground improvement in construction. Ground improvement encompasses a range of techniques employed to enhance the engineering properties of soil and rock. These properties include shear strength, stiffness, permeability, and compressibility. By improving these properties, ground improvement techniques create a more stable and predictable foundation for construction projects. The necessity for ground improvement arises from the variability and often unfavorable conditions of natural ground. Factors such as soil type, density, moisture content, and the presence of groundwater can significantly impact the ground's ability to support structures. For a comprehensive understanding of ground improvement techniques, Ground Improvement by Klaus Kirsch and Alan Bell serves as an invaluable resource. This book provides in-depth insights into the principles, methods, and applications of ground improvement, equipping engineers and construction professionals with the knowledge to make informed decisions. Ground improvement covers a wide spectrum of topics, from traditional methods like soil stabilization and grouting to more advanced techniques like vibro techniques and deep mixing. The book also delves into the selection of appropriate ground improvement methods based on site-specific conditions and project requirements. Whether you're a seasoned engineer or a student entering the field, ground improvement offers a wealth of information to enhance your understanding of this crucial aspect of construction. Soil stabilization stands as one of the most widely used ground improvement techniques, aiming to enhance the strength and stiffness of weak soils. This method involves incorporating stabilizing agents into the soil to improve its engineering properties. Cement, lime, fly ash, and bitumen are common stabilizing agents. Cement stabilization, for instance, involves mixing cement with the soil, where it reacts with water to form a hardened matrix, significantly increasing the soil's strength and stiffness. Lime stabilization, on the other hand, reduces the plasticity of clayey soils, making them less prone to shrinking and swelling with changes in moisture content. The choice of stabilizing agent depends on factors like soil type, the desired level of improvement, and environmental considerations. Soil stabilization proves particularly effective in improving the bearing capacity of weak soils, making them suitable for supporting foundations, pavements, and embankments. Section 5. Grouting, filling the gaps for enhanced stability. Grouting involves injecting specialized grouts into the ground to fill voids, seal cracks, and improve the overall strength and impermeability of the soil or rock mass. This technique proves particularly useful in karstic regions or areas with fractured rock formations. Grouts typically consist of a mixture of cement, water, sand, and admixtures tailored to the specific ground conditions. Depending on the project requirements, grouts can be designed to have varying viscosities, setting times, and strengths. Grouting finds applications in a wide range of projects, including stabilizing slopes, underpinning existing foundations, and creating underground barriers to prevent water seepage. By filling voids and strengthening the ground mass, grouting enhances the stability and safety of structures built on challenging ground conditions. Section 6. Vibro techniques, using vibration for ground improvement. Vibro techniques utilize vibration to densify granular soils, improving their engineering properties. Vibroflotation and vibrocompaction are two commonly employed vibro techniques. Vibroflotation involves using a vibrating probe to create vertical holes in the ground. As the probe penetrates the soil, it displaces and densifies the surrounding granular particles. The resulting compacted columns of soil enhance the bearing capacity and reduce the settlement potential of the ground. Vibrocompaction, on the other hand, uses vibrating rollers or plates to compact granular soils at shallower depths. The vibration causes the soil particles to rearrange, increasing the soil's density and stiffness. Vibro techniques find applications in improving the ground conditions for supporting embankments, storage tanks, and other structures constructed on loose, granular soils. Section 7. Deep mixing, creating composite ground for superior strength. Deep mixing represents an advanced ground improvement technique that involves blending the in-situ soil with cementitious or other stabilizing agents to create a composite material with enhanced engineering properties. This method proves particularly effective in soft clays and silts. Deep mixing typically involves using specialized equipment with rotating augers or paddles to blend the soil with the stabilizing agents. The resulting soil cement or soil lime columns, often arranged in a grid pattern, act as load-bearing elements, increasing the bearing capacity and reducing the settlement of the ground. Deep mixing finds applications in a variety of projects, including supporting high-rise buildings, bridges, and wind turbines. This technique offers a versatile and effective solution for improving the ground conditions in challenging soil profiles. Section 8. Real-world applications: ground improvement in action. Ground improvement techniques have been instrumental in numerous construction projects worldwide. The iconic Palm Islands in Dubai stand as a testament to the power of ground improvement. Vibrocompaction and dynamic compaction were used to densify loose sand, ensuring stability. The Oresun Bridge showcases ground improvement in challenging marine environments. Deep mixing techniques improved soft seabed soils for the bridge's foundation. Kansai International Airport involved sand compaction piles and deep mixing to improve soft clay soils. These examples demonstrate the versatility and effectiveness of ground improvement techniques. Section 9. Benefits of ground improvement: cost-effectiveness, sustainability, and safety. The benefits of ground improvement extend beyond simply creating a stable foundation. These techniques offer significant advantages in terms of cost-effectiveness, sustainability, and safety. Ground improvement can often prove more cost-effective than alternative solutions, such as excavating and replacing unsuitable soils. By improving the existing ground conditions, these techniques can reduce the need for costly and time-consuming earthworks. Ground improvement techniques contribute to sustainable construction practices by minimizing environmental impact. These methods often utilize locally available materials, reducing the need for transporting large quantities of fill. Additionally, ground improvement can reduce the carbon footprint of projects by minimizing excavation and transportation requirements. By enhancing the stability of the ground improvement techniques contribute to the safety of construction projects and the long-term performance of structures. These techniques mitigate the risks of settlement, landslides, and other ground-related hazards, ensuring the safety of both construction workers and the occupants of the completed structures. Section 10. Conclusion. The future of construction rests on solid ground. As the demand for infrastructure and buildings continues to grow, so too does the importance of ground improvement techniques. These techniques play a crucial role in enabling the construction of safe, sustainable, and cost-effective structures, even in the face of challenging ground conditions. From traditional methods like soil stabilization and grouting to advanced techniques like vibro techniques and deep mixing, the field of ground improvement continues to evolve, driven by innovation and the need to address increasingly complex geotechnical challenges. Ground Improvement by Klaus Kirsch and Alan Bell serves as an indispensable guide for understanding and applying these techniques, empowering engineers and construction professionals to build a more resilient and sustainable future, one structure at a time. As we venture into an era of unprecedented construction demands, one thing remains clear: The future of construction rests on solid ground.